Okay, this is the final lecture for the review section, except for chapter 10, which is the complex variable chapter. We'll do that next week, but today I would really like to make that connection more solid between the quantum mechanics and the classical mechanics. And the key person in that is a rascal named Jacobi, who worked with Hamilton. And the Hamilton-Jacobi equations are the classical version of quantum mechanics, really. And we'll talk about that toward the end of this lecture, but the basic idea of a Hamilton-Jacobi equation is to handle systems of trajectories, such as the one we've already given to you as a homework, the volcano and the atomic clock. Really amazing piece of engineering for cesium atoms that just to interrogate the very top of the envelope where there's no Doppler shift, and therefore give you a very precise time, which I'm looking at on watch that goes to the National Institutes of Standards and Technology. So that will be one of the things that I would like to make a big deal about. And the this character here, I really am impressed by the hairdo. How long did it take to grow that much hair? Or did you just buy it as a wig? I don't know. It was quite fashionable. And this is the late 1600s. They worked on what we're going to talk about today, and that is one of the improvements to a pendulum clock that I like to say it saved physics, because pendulum clocks, as we looked at very briefly in the last lecture, are not all they're cracked up to be, and they very quickly get out of sync. So one of his creations is recreated on the wall, and we'll look at the simulations of that here. Got another thing I'd like to show you, and this is the use of phase space to sort of control something. It's just a brief vignette here called Catcher in the Eye. Does anybody know what that's referring to in the literature? J.D. Salinger.
Catcher in the Rye.
Catcher in the Rye. Right.
Good book.
We'll see what that means in mechanics. My apologies to J.D. Anyway, the whole idea of phase space and action and all of the things that are really now called semiclassical mechanics are the topic of this lecture. Now, I think what I probably ought to do is, we talked already about this particular occurrence, this thing enough, and also in this lecture is a sketch of what I had in mind for your problem that you did or have, I hope, done already. Just for a brief moment here, and this is on the last screen, I'd like to show you the oscillator. Get this thing on the lecture again and get it playing. The oscillator animation, and this, I haven't tried this link actually on this particular machine. Let's just see if it works. And I need to go ahead here to where I really need that. Yeah, this is it. Go on. If this works, it's quite beautiful. So it starts out like the volcanoes of Io, except we're inside the Earth now, and it's an exploding neutron star in our fictional representation. And what I'm doing with the color is very important, and that's going to be the last topic of this lecture today. What we do is we color the trajectories according to the value of the Lagrangian, and since that is related to the quantum phase, what you get is a color outline of a quantum wave function. This is a really sneaky way to solve quantum mechanical problems that was discovered by Rick Heller. I had a hand in that too, and the coloring of a trajectory was not what they were really emphasizing. What they were emphasizing was dragging a little Gaussian wave packet on each trajectory. The computer can do that easily, and phasing it according to the Lagrangian and just summing all of those up to make a wave function. And then you autocorrelate that and you get the spectrum. So you people should keep this in mind, because there probably are quantum mechanical problems that are really hard to solve by ordinary matrix methods. This is an alternative that is very powerful. And it happens that this one goes on giving the phases. If I resume this particular animation, it will just keep doing it. But that's, I think, a really cool example of a family of trajectories, very organized one, and this is a high symmetry system, so we get to do this very easily. It's done in one pass, essentially. But then it just keeps on going. This is what the mechanical effect would be if you had an explosion. Assuming that these objects, when they come together again, can go through each other. And of course you assume that when you're doing the classical trajectory analysis, so that would then give a wave function for a harmonic oscillator. You can check that very nicely against, in this case you can do that analytically. So, I'll pause that. The picture here is another example of that. And this particular slide, and the one that's at the end there, shows the controls that you mess with, and the controls are right out in front. If you go click that, you get the controls to come up in that form. This is an older version of this particular program. Okay, we've got a bit of work to do, though. I would like to make sure that we understand just the single dimensional harmonic oscillator, and so I want to go over again this particular vignette of algebra and geometry. And so I will get this on all three screens so that we can take a look at that. This particular one right here, I think, is ready to move as well. So I will do that. And that's what we're after, is the Hamiltonian plotted in terms of its coordinate and its momentum. It's two-dimensional in that sense. It's a one-dimensional oscillator, a one-dimensional pendulum. But that makes it a two-dimensional phase space. The coordinate and the momentum are the x and y axes. And then the z-axis, presumably coming out of the screen there, that makes the three-dimensional figure, is the Hamiltonian as a function of those two quantities. I'd like to spend some time with this particular geometry. This is a Thales geometry that lets you see clearly what variables are most efficient for describing the elliptic integrals that give you the very weird frequency dependence on amplitude that this oscillator has. So this is not a harmonic oscillator except for very small amplitudes. And that is, I think, pretty obvious just from looking at this thing. Here we have P momentum of the angle theta squared, but here we would have cosine of theta, that would be theta squared over 2 if I just took the first term of the Taylor series expansion of cosine of theta. So it's a harmonic oscillator only when I can ignore theta to the 4th power and 6th power and 8th power that would come out of a Taylor series from that cosine. So what if you can't ignore that, then what? Well, we've got 2 alternatives that we're going to talk about with regard to pendulum. And the first will simply be the anharmonic one. But then the remedy to that Mr. Huygens discovered, and he only really figured the whole thing out about a year before he died. So he spent his whole life sort of with this in the back of his mind. Also realizing that it's such an important piece of physics to get the timing right, be able to time astronomical events precisely. So it is that was his major trump. But this is a really smart guy. He really invented calculus just sort of in his spare time. And he didn't challenge Newton. He was somewhat timid. And he was, of course, much younger. Newton was a big guy in the Royal Society, and Lycans was just trying to knock on the door of the Royal Society and get in. And he did a much more elegant job of developing calculus just on his own. So that's just a bit of what he is. The other thing that he's famous, we've already talked about, is the Huygens contact transformation that describes wave motion in a geometrical way. And I'm going to go into that again as well. Okay, so let's go ahead with a little bit of this. I've already pointed out, I think, that this is another way to think about Hamilton equations. They've got this anti-symmetry structure. They've got a cross product in there. The motion, that is the time derivative. And let me use the center screen here. We'll get these things all synced up here. That bottom line there, this q dot p dot equal, well, it's not just the partial with respect to p and the partial with respect to q. That would be a gradient of h, but we've got a minus sign in there. This is the z unit vector, the unit vector along the vertical direction there, cross the gradient. So the idea is if you're on one of these trajectories going around, okay, and the trajectory, like a phase space, has to be, as I pointed out, left-handed, Hamiltonian. The idea is that at any point on that phase curve, your speed is going to be determined by the gradient, but it won't be like falling down a hill. You're going to stay on that curve, but the gradient, this perpendicular to that, is what's giving your speed. So that's a sort of a funny way to look at this, the very simplest but not trivial Hamilton equation of motion of a pendulum, an anharmonic oscillator. So I point this out. This is EH cross the gradient with a minus sign, so we get the left-handed motion. Okay. So basically, the h-axis cross with the fall line. You're not going to go down the fall line according to the gradient. You're going to stay perpendicular to it. If you know about, how many people here have skied on a snow thing? Just out of curiosity. Not too many skiers here. Anyway, one of the things that you do when you're on a steep slope is try to get off this slope, and you go along perpendicular to the fall line, but this slightest down or up, and you start to speed up, right? And it turns into a disaster. Some trees on the other side. But anyway, That's basically what we're talking about here when we talk about the cross product with a gradient. That's determining your phase space motion, and that's Hamilton's equations written in a fun kind of way. Okay, let's see if there's anything else I can say about that. I think that's about it. So this is a sort of phase space curve, and of course it doesn't just contain the valley. As soon as you get above what's called a separatrix, a separating curve, that red line there, as soon as you're outside of that, then the pendulum is having velocity as it passes the theta equal pi. The unstable balancing point of this thing is right there, right at the intersection of the separatrix curves, separatrices. Okay, so get used to the name separatrix. It's going to show up in other things that we do. That has a flow this way on this side here that matches the flow right there. Then the phase flow coming back here. That's continued down on this side. So eventually you get so far up from this that the valleys don't matter anymore, and you just get linear rotation, linear description of rotational motion. So if you get a pendulum that's really going fast, the gravity isn't affecting that thing very much. That's true classically and quantum mechanically, and that's an interesting thing to think about with respect to this particular archetype of oscillator that's not harmonic. Okay, what's next here? The elliptic functions. So this is the dull part of this lecture, the algebra, but the elliptic functions are really something that needs more treatment. We're not going to do it here, but we will hopefully get to some discussions of that. If any of you know Brad Clay, that's his deal. He's really noticed some interesting things that mathematicians have done with elliptic functions that make some sense out of them. We're just going to define them for today. So here we have just what we got as a Hamiltonian that's constant. That's what's making those level curves in the picture of the valley and saddle point and all of that. The main thing here is to be able to just write the equation directly, but then since this is constant, I can integrate that and give time as a function of coordinate. Now, of course, what you'd really like to have is the coordinate as a function of time. So we're used to doing that with harmonic oscillators. The elliptic function is the solution to doing it here. So that is what we need to look at. So we're looking at an integral. It's kind of weird. This is, as I said, this is an example of a quadrature integral, an integral that is being taken over a quarter of the oscillator, the quarter of its total trajectory, and this is this is an integral over angle, and this is an integral over time. So we're looking for travel time just from 0 to a particular amplitude, a particular value, and that value would be, if we were talking about a loop like this, would be a quarter of the way, okay, through an oscillator, a total period tau. So the idea is to make that integral something that we can deal with, and that's where the geometry comes in, the geometry of energy. This is a Thales geometry construction, and there's a little rectangle in there with a 90-degree angle that goes with any point on the circle that subtends the total diameter. And this is half of the angle of this. So, nice way to display the half angle. And that's the transformation that we're going to do here. Use the half-angle coordinate to make a doable integral, make this integral something that is worth talking about and tabulating and all that sort of things. So writing this thing in terms of the epsilon angles is the key to it. So you end up with something like this, and that can be rewritten just as a 1 minus k squared sine squared of epsilon. So that's an elliptic integral right there. That's it's called the elliptic integral of the first kind. There's a whole bunch of others that you can define for other purposes, but this is what we need for for the pendulum. So normally we wouldn't include something like this in a review, but I think it's important to see that it's there, and also make a connection of this with the case that this were suddenly to become a harmonic oscillator. If I were to do that, if I were to get this thing just to be epsilon squared, that's just what it is for very small epsilons, then I have the integral that gives the arc sine. So I have this time here coming out to be an arc sine of the, well, it's an arc sine of the epsilon that you end up with. That, for very low amplitudes where the sine of epsilon is epsilon, that reduces to that reduces to a quarter of the 2 pi period. So that is just to let you see a connection between what we would call an analytic solution using the sines and cosines using trigonometry. At this point you realize that for me to do this, and I'm talking about doing it in the 1600s or the 1700s, you'd have a table of sines, right? Otherwise, what good is this thing? So somebody had to go through there and for each value make the numbers, right? Here, we're a bunch of lazy bunks. We just go on the sine button, right? Well, the problem is that most calculators don't have an elliptic function button. I finally found one that did. It had actually all 3 kinds of elliptic functions. You literally push a button and you get the elliptic function. You had to put in a couple of variables in order to work, because that's what most elliptic functions are defined that way. But the AM function this is the AM inverse function, and that's the amplitude function is called. That is, let's see if I got everything I need to have here. Anyway, that reduces to the sine. That particular function reduces to the sine. So get it on this one down here as well. Okay. Don't think there's much else I need to say, except it's worthwhile one more time just looking carefully at what that AM function is with a simulation. And I'm going to try to do it on this machine. I may come back, this one works actually a little better, but let's go ahead and that's what we're going to be getting. I'll put that up here just as a reference in case this one doesn't work. You see what we talked about actually last time. And we'll do this one too. That's what I want to do. I want to show Huygens pendulum. In any case, I start this one out with an amplitude that's pretty close to the top, that is pretty close to the top of the saddle point in that weird surface that goes with this one, and I might as well make use of the other projector here and get that picture up there, realizing what you're doing as you oscillate through this system. As you, I can't use the blue, I better use the green to point out here. And these things are, there we go. When you get to the saddle point, if you get right exactly on the saddle point, that means you have this thing balanced just perfectly. And I mean really perfectly, and quantum mechanics doesn't exist so that it can really be perfect. You sit there forever. But boy, it's really hard to balance this thing. And I can get within a pixel of the top here, okay? Instead of stopping where it does, I'll stop a little closer, okay? Now we're starting to see the elliptic function forming there. And the other thing that's happening in this simulation is we're taking the Fourier transform out. Okay? And that's another part of mechanics, is just to Fourier transform everything and solve those equations. We'll occasionally resort to that when we can. And Keller's way of doing quantum mechanics is to let the classical mechanics be Fourier transformed and then do the quantum mechanics automatically. This is all really neat stuff. So I'm going to try to get within a pixel of that thing there. Now I see 3.12 radians, so I'm not 3.14, but I'm still pretty well balanced for a long time. And then it repeats that, you see. When it comes around the other side, it also hangs up at exactly that period of time. So you're getting to see the AM function pretty clearly there. And it's kind of a square wave, right? If I could really, get within a fraction of a pixel there, I could make a big square and then whoop, another big one, whoop, and so forth, right? And then I could rescale that back to the point where it really starts to look like a square wave, right? Anyway, the Fourier transform is starting to look like the Fourier series for a square, right? And what's that? You remember the coefficients for that? Okay. 1/3 minus a fifth plus a seventh. Okay, so we have a harmonic series of Fourier transforms alternating here, up, then down, then you can barely see it there, up, but it's 1 over, this one starts off 1/3, this one 1/5, this one 1/7, and there'd be a 9th if we waited a really long time here. Okay. But, and of course it isn't quite a square wave, so this is kind of a smoother Fourier series than it would be if I could get the thing to really hang up there for a long time and then rescale it. Okay, I'll try one more time here to see if I can get it, right within a pixel 3 point. I'm sort of messing with it a little bit here.
You're also giving it a velocity.
Yeah, that's not good. Let's let her go and see if.
Yeah.
Okay, now this, you see what happened. I'm just a little bit on the other side. I took off, right? Let's try again. That's not good. I'll just, re-punch it here. 1, 2. That's what we had before. I was hoping to get a 3-1-3, but I don't think I'm going to be getting that. That's just what we had before. Okay. Now, when you play with this thing, you can always use a bigger scale. You can use a finer screen. All kinds of tricks that you can do to make a really clearly square elliptic function. Okay, now remember all of the other possibilities. If I started here, they look closer to being cosines, and they're really fast. And as you get down, say this one right here at 90 degrees, okay, almost beginning to look maybe a little circular, and so forth. The closer you get to the bottom, the more circular you get, and the closer you get to having an actual trigonometric function, in this case the cosine of the frequency of the pendulum in its limiting case of being, and you can see that one is the zeros for the last two that I have done are commensurate for the first 5 or so oscillations. Okay. Now what Huygens wants to do is make this pendulum work for all amplitudes available and have the same frequency. So that is the next topic. But any questions about this before we go on to that one? So the next stop here is a very strange looking pendulum. Okay, and as I say, we have reproduced in this room, and you can play with it, but there's two pendulums actually on this. I guess I better go and make use of this screen here. So the laser seems to have stopped pointing here. I will come back on this to this guy and put this right here. So what there are over there, and as I say, there are two lead weights, fishing weights, stuck through threads, one of them a little bit further out so that it doesn't wrap around a cycloid curve. It just makes a circle, and there's the circle that it would follow. See that little faint line right there underneath? That's the ordinary pendulum. The ordinary pendulum follows that track right there. Well, if the pin could hold it, it would go all the way around, but we'd only stop the thing about there. The cycloid is limited in its angular amplitude, but not in the coordinate that we're dealing with. But anyway, this dark curve here is a cycloid made by a point on a rolling circle whose curvature gets less and less and less and less until finally, and it's really hard to see that, but it kind of has a little kink on it so that it ends pointing straight up. That's something you might not have known about a cycloid, but its curvature is going to infinity right there. Okay? The last thing here, the string, the weight is going to be wrapping on that up point, making a small circle and vanishing a small radius circle. So, not much difference between these curves, and you can't see any difference all the way out here at about 30 degrees or so for the ordinary pendulum. But boy, does it make a difference in the dynamics to do this. Okay. So, let's go ahead on this screen, and where I have control of the thing, we're now going to talk about when he wasn't having his hair done, this is what he was doing. Okay. We're going to make a simulation. And actually a simulation that I might as well start off with. I want to show you the geometry of the two cycloids. And that's what's interesting about this, is when you wrap a string around a cycloid, and there, the cycloid with the pins in it is this curve, and we're wrapping a string around that, and there's a string unwrapping, and it's got to that point right there, okay, for it to be actually on its cycloidic path. This is the same curve, except for translation, as this one. This one would just be another cycloid. This is the, when you unwrap a string from a curve, you make another curve that's called the evolute. And anybody in calculus have studied evolutes in any of your courses? Do you remember doing that? How many people, just out of hands, have seen evolute, involute? Well, Monson, the only one, I guess. Anybody else? Again, you're being cheated. This should be in there. And the opposite of that is looking with a particular curve for a locus of the center of curvature. That's the opposite of wrapping a string around and making this one. Then I take this one and I look at each point. I draw a radius perpendicular there and the radius of curvature. And you can see what the deal is. If I have a string coming from here to here, the radius of curvature is the length of that string. Anyway, this curve is called the involute of that one. And these are all things that people in mechanics knew so well. People like Huygens and so forth. And it's, we'll be talking about things like that. So, what's cool about this is that when this is making, there's a pair of circles that roll. This circle rolls on this ceiling right here, and this circle here rolls on this ceiling, and the two of them together make both cycloids at once. Okay, that's what we'll see in the animation. Okay. And then we'll try for getting things like that. That's the curve. It looks like a bunch of straight lines. We're getting the sawtooth function instead of the square wave function out of this, if we're lucky, if we can get out to the extremes. So, maybe what I'll do again is put this on the screen here, and I'll leave the picture of the thing down there so you remember what that everything means. Let's just go ahead and see if this will go. Yes, there we go. Now this is a really jerky phase space when we're close to the amplitude. Now let's start here with smaller amplitudes. For example, let's just try a half. Okay. That's not too different from what we would have gotten if it was just a pendulum. You see, the thing is only wrapping up to about 4 or 5 pixels up in here, so it's really just like hanging the ordinary pendulum. And what Huygens did first, and this was when he was really young, is he said, you know, the way we can improve pendulums is just put 2 circles. You know, he just had a little circle there, and he had to figure out what the circle radius should be, and that's how he corrected the pendulums that have his signature. That's the Huygens correction. He didn't, as I say, until he was about to die, figure out that you needed a cycloid there. Okay, but it's essentially a circle to start with. And so as you go to higher amplitudes, you need more of an arc. If I go out here to amplitude 1, okay, now I'm wrapping more. I'm trying to speed this pendulum up by making it a string shorter, but doing it in a variable way, right? When it's right in the center, I'm not trying to do anything to it, right? But when it gets out to the edge, it's getting sped up by having to climb the wraparound, okay? And you can see, unlike the ordinary pendulum, by the time I got to this amplitude, they were not crossing at the points down here, right? This one is. This one, every amplitude I put on this thing is going to have exactly the same frequency. And this will be a problem you solve later on. It's one of the many properties of the cycloid that they're kind of all ganging up on you on this particular device that Mr. Huygens came up with. Okay, now we're getting to the point where it's jerky, really jerky. And I'm going to try to start it right on the very end here. It's a little risky because now I'm really at the mercy of what a pixel can do to me. If I can not be nervous and catch it. Oh, that's not going to work. That's just going to be another one of the curves I have. What I might try doing, I've forgotten how this works the best. I might try going out here just a little bit on the edge here and see if I can get it to go. Bam. There we go. So with this model here, this is showing you that if you had some way to make a pendulum out of a tin can that was magnetized so that it would roll without friction on a ceiling, the velocity of the tin can rolling is constant. Then all of a sudden it reverses. Bang, bang, bang. Isn't that wild? So this is an extreme case of an oscillator phase space. And it's not a harmonic oscillator, but it does have the property of a harmonic oscillator of being independent of the amplitude as long as I'm inside the cycloid. Okay, I'm limited by whatever geometry this thing has. But all of the amplitudes have the same frequency inside that domain. Okay, that's, you know, it's this kind of stuff that makes classical mechanics fun. Just knowing the history of it is fun. Okay. It's really a beautiful thing. And what would be the quantum mechanical equivalent of this? That's not an easy thing. We're thinking molecular chains and all sorts of things. That's for another day. Okay, now, what kind of Fourier transform are we getting? We're getting the Fourier transform coefficients here pretty much of a sawtooth. Do you remember how that goes? It goes as an integer squared in the denominator. You got 1/3 squared, 1/5 squared. Well, by 1/5 squared I can't even see it, right? And I've been running this thing for a while. You let it run all day and you'll start to see the Fourier components pop up there. But it's 1 over an integer squared, so I really only have this one. You just barely see a little bit of a dimple in the other. Okay. Well, more analysis of this to come later, but I thought you ought to see it right off the bat while we're talking about things that Huygens did. And there's a whole heck of a lot more things that we need to get. Now, I guess it's time for us to do just a little bit of the catcher anyhow. So if there are enough questions about this, I will bring this one to a halt. And that is that. Let's get out here in the lecture and go forth. And we've had this homework problem already, right? This is where we look at where the bottom of a parabola that represents the result of shifting the origin. That is, we originally had an oscillator that sat here, and we decided to add an electric field. Okay, a big electric field, so that it didn't just move, you know, a little bit this way, a little bit that way. This one was enough to take the whole parabola and bring it down, and in fact follow a path. The bottom of the parabola follows a path that is just the same as this curve turns upside down. I think most of you got that problem, but now we're going to look at it, and we're going to do a simulation where we play with the amplitude, that is, we'll the amount of the electric field, but also we'll play with the frequency of the parabola. Make the parabola have a high frequency, or make it a fat thing that doesn't have a very high frequency, and play with the amplitude for that one. So let's see if I can get that going. What I guess I'd better do is maybe use that particular screen. So this is the simulation that we'll see, presumably, if I go ahead and turn this on. There we go. Okay, so the deal here is I can change the electric field, QE here, and I've got to fix it so that not changing the spring constant too much, but I could certainly do that. See if I'm a little worried about what the thing is. There we go. So there's a starting point right there. I can make the spring stronger by going here. And the idea, you see, is to catch this thing in the phase space. Think of it as a hurricane, and there's the eye of the hurricane right there. If I want to catch that thing, the idea would be to put this object. And this is really kind of hard to do. But what I would like to do is go over there and try to catch the thing near the eye missing. I'm just making it oscillate about the same amount around a new point. But maybe if I come in, whoop, I went the wrong way. When I come in, try to get it, there I go. Okay, I caught it. Now it's in a lower amplitude. So that's an example of deresonance. What normally happens with it when you play with this thing is, and let's just go and start. One of the things you can do here is just reset the thing so it's right in the center, but I'll let it oscillate a little bit there. I've got it so it's calmed down, but what I can do is go like this, swing the thing over there, and then go on the other side, swing it over here. Well, you can see what's happening. I'm going to be out of control. At that time I managed to reduce the amplitude by going just the right motion. Okay, so when I get over here and try to get the thing in the eye, I got it stuck oscillating off the origin and with not much amplitude. So this is, I hold this up to you as something that could be engineered, should be engineered for anything that involves controlling an oscillator. Now the other way to control it is to go this way. This is parametric amplification, and we're going to study that later on. That's a simulation called Jerkit, which we'll make a big deal about later on. But this is just the beginning of thinking about using phase space as a way to capture something or use it very effectively and easily to amplify the oscillations. Okay. All right. So that's the end of our discussion today of the classical applications. Now what I want to do is go into the behind the scenes, the deep state of physics is quantum mechanics. Okay, and that comes next year. So let me make sure I pause this thing before I get out of there and go on here to a weird derivation of Lagrange's equations. So what does that mean? I'll bring this one out to space. What that means is I want to discuss variational calculus. Now this is really something that's in Unit 7 of this particular course. I've pushed that kind of discussion to the very end and then realized that it's got to be in the review too. So here we go. In just a couple of lines here, I am going to derive, and derive in quotes because it's a crazy way to do it, and we've got to explain that craziness. But as I say, this derivation quotes is very short, and it's also something that you should probably know about from a good calculus course, and that's the calculus of variations that would be in what, Cal 3 now? I don't know. Is it? How many of you didn't see it in Cal 3? Again, being cheated. it should be. I mean, calculus variation may be off in another course entirely. But the deal here is that I have this Lagrangian function of coordinate and velocity, queer coordinate, queer velocity, but whatever, could be x's and just ordinary variables. The idea is that this thing, which would be called our action, this thing, I'm going to try to find extreme values for that. I'm going to minimize this thing by adjusting every point, and this would be done digitally by, say, having 20 points here, and I'm able to jockey any one of them. They're independent. I can make this one up, and that one down, and this one up, and so forth. Or I could just have a continuous variation. That's what the makers of this calculus of variation had in mind. The idea that some function, delta q, so this is a function that varies continuously from this point to that point in the independent variable. And so I'm trying to figure out how could I make this particular integral come out to some extreme value, either a minimum or a maximum, for some curve in here. Maybe the curve that does that is up here someplace. I'm going to try to find it. I'm going to try to locate a particular curve, or of all the possible curves that would connect, say, this particular something at this particular time and some other thing. I'm not going to move those two values right there, and I'm not going to move these times, but I'm going to play with everything in between. So the demand to not vary at the boundaries is this form, and that's key to this derivation. But beyond that, it's just a matter of doing an expansion, and just a first order expansion will imagine that these things are actually a few pixels that we're working with on top of some curve that we already have defined, hopefully close to the result, which is the extremum. So I have an integral written out here by varying this thing, by not just varying the actual position that this thing has, but I also vary the slope of the thing, the velocity. I'm going to vary the velocity as well. These are independent parameters that I get to jockey around. And I will demand that the one with a dot on it is correctly defined as the first derivative with respect to time. Okay? So, to do that, and to make the thing actually work, I'm going to replace this guy right here. This is one that involves the velocity, with a dot on it. I'm going to replace that using the product rule. Okay. Now remember, the product rule derivative, actually a twisted version of it, where this is on the other side of the equation. We got u dv here, and then we got minus duv. That was exactly what we did in the later stages of the development of the Lagrangian equations, right? Well, we're doing it here too, but we do it once and we're home here, okay? So we replace this guy with that stuff right there. So having done that, we get a simpler expression, actually a very simple, much simpler expression, if we make use of the limits that we've placed on this thing, namely that thing right there. But this is what happens when we replace this guy with our thing. And we take it outside, we make the integral right here, and realize that we've got an integral here of this thing, and then the derivative of it, so it's just going to be that thing. That's what you're going to get there between the two limits. Okay, that's what's going to happen right there. And when that occurs, you see, that's when I need to make use of this. I need to demand that my velocity is 0, that's no slope, and my difference from the curve that I started with is also 0. So we're going to have those delta Q's, those variations, just disappear completely at the ends in our variation. So this is a very special kind of variation with respect to the ends. Otherwise, in between there, we have quite a bit of freedom. So requiring that just gives me this. So there's what we've reduced this thing to is just first order variation. If you could take all of these quantities, you know, in the way we have. And the deal is that this will leave the thing, when I do this, in a minimum value. Actually, that's what it turns out. That's something you have to prove. We'll skip that for now. It's either a maximum or a minimum. Some sort of extreme value occurs if I make this 0 all throughout. If I make the curve just exactly so it fits this. And what is that? Euler-Lagrange equations. Now the way this is expressed in Feynman's Volume 1, and this is one of the few places where they put a verbatim lecture into that book, where they have him talking about his high school teacher, Mr. Bedar or something, okay, who says, Feynman, you looking a little bored? Let me tell you something that's really interesting. And any of you who've read that part know what I'm talking about. He talks about how all of the things in nature fly according to an equation that keeps this Lagrangian. He has to tell you what the Lagrangian is, but you already know kinetic energy minus potential, right? So everything flies, so to keep the integral of that thing minimum. And Feynman says, oh, that's really great, that's really neat. And of course, at that point in the book, he doesn't say, WTF. Why is nature so inclined to fly just so you minimize this thing called the Lagrangian? What the, as I say, WTF, okay? The WTF is the whole story of quantum mechanics. We're minimizing a phase integral. And that's what I need to talk about now, okay? And that's where Hamilton-Jacobi and all that kind of stuff comes in, all right? So, here's where we learn about Hamilton-Jacobi equations. And it's a good time, because they're really key, they're really crucial. Let's get all of the stuff that we've worked out so far up here with regard to the Lagrangian and the Poincare-Legendre transformation. The transform between the Lagrangian and the Hamiltonian. Or flip them around. That's the way I've got it written up there. This becomes Poincare. Poincare is really the person that made this, made sense out of this most clearly, and he sort of intuited it, and he's the one that I told you about that frustrated, he's a Feynman-like character, frustrated his students. I just say, what's the matter with you? Can't you see that this is true? All right, you dummy. I mean, I don't think he did that, but, you know, it isn't very difficult to make that sort of atmosphere, right? And ask now what we're dealing with here. When I go LDT, I put a DT on each of these guys here. Right away, the velocity, which is defined as dr over dt, implies that ddt is dr, so that's what we're dealing with right there. And then the dt for h is sitting there as well, okay? That's when you, as a wave person, recognize that this thing that we're looking at is what is called the quantum phase. So when I say L dt, what I mean is ds, where s is this action integral of L dt. And this is the integral that we're going to use to color our curves so that the action phase shows, the actual value of the quantum phase shows on a classical net of trajectories. So here's kind of where the pebble meets the metal, or the rubber meets the road. The PdR minus HdT, that is the differential of this thing called action, really key. Now we make a big jump to 1900. That's this one, sort of reduced version of Planck's axiom that the total energy, we know Hamiltonian, is that, but we're setting it equal to a frequency with a scale factor. And 21 years later, de Broglie decides that this has got to be done as well with the same scale factor to the, not just the per time variable, that's frequency there, angular frequency is a 2 pi hiding in that, and there is one in that one too, but also in the k, the per space variable, the number of waves per meter or per centimeter is actually a Kaiser, and that's where the k comes from. And we'll talk about all of that toward the end of the course when we really put this stuff together in Unit 8. We're going to have to jump to that when we have the last few weeks here. You can look ahead, of course, online and see all this. But anyway, this is de Broglie's relation, this is Planck's relation put into this, and you see pretty quickly, probably can already, that that's the phase right there. That's kr minus omega t. That's the simplest wave phase. Got a certain k vector for the wave, and could be one-dimensional, in which case we would need to use thick printing here. And then here's the angular frequency times time that you'll always have, no matter what dimension you're working with. Okay? So, and psi is the letter we use to describe that. That's a plane wave. That's the simplest quantum mechanical eigensolution for something in a vacuum, basically. No potentials around if you don't want to have them. Okay, so this could just be a kinetic energy, and we'd be doing our quantum mechanics, our very baby quantum mechanics, correctly here. Okay? Now, the question is, though, can you do this integral? Can you actually get this integral to give you a function? Differentials aren't necessarily integrable. The answer is that a differential is integrable when you have as a coefficient of the dx something that is a partial derivative of the function that's actually going to come out of that integral. And the same thing for the y part of this. You need that. Now, where does all that come from? How does that connect? Well, just take yourself, and I should be going ahead here on both of these screens because some of this writing gets kind of fine. So let me get up to that point, and then I'll point up here what it is I'm looking at. These conditions, the zero curl conditions that we're going to make a big fuss about when we study complex variable analysis of fields next week, similar to conditions for integrating work differential, okay? Let W be your good old force dot position differential, F dot dr, okay? You know that that potential, that meaningful potential only happens if the curl of that field is zero. Or stated another way, the partial derivative of the x component with respect to y has to be equal to the x derivative of the component y. So here's the y derivative of the fx, it has to be equal to that in order for the curl to go to zero. Or, and here's a really easy way to state it, forget curl, I just want a partial derivative that obeys the rule that we gave on the very first day when we talked about these. Remember the boathouse, right? the boathouse way of describing how partial derivative of respect to x commutes, giving the same value. If this is true, in other words, coming up on the x path to the top of the boathouse gives you the same result as if you go the y path, you meet in the same place, right? But if you have a rotten boathouse where the roof is falling on one side but not on the other, that's not true anymore, right? And that's the situation you have with multi-valued functions, and you won't have a single function. You won't have a closed integral for this. Well, the same thing's true for doing our phase. So we're going to have unique phase everywhere in order for actually get something from this integral. And that's a key idea. I mean, that is really important. So here are those conditions. P, right here, has to be the partial derivative of the thing we're after here, the action, with respect to R. In other words, P has to be the gradient of the S surface, whatever that happens to be. Okay? And then I got a minus h here. That minus h has to be the partial derivative of the S with respect to that variable, t. So here you have a single line derivation of these really important, for quantum classical interface equation, the Jacobi-Hamilton equations. Now if you go to a book like Goldstein, it takes him about 45 pages to prove this. This is a lot shorter than 45 pages. They say Goldstein's a great mechanics book. It's a piece of crap, because it has many things like that. The guy's an astronomer. He's not he doesn't do mechanics. The Russians are the guys that know this stuff. And so Landau Lifshitz, that's a good book on mechanics. It's only about that thick. Okay, so that's what we're dealing with here. And this is really kind of neat. This is how a classical mechanic, even a garage mechanic, could derive quantum equations. The ones that you struggle over when you first learn the subject. Just say that we have a wave like that. What sort of relations would you expect it to have? You'd expect it to have Hamilton-Jacobi away, if you believe what I've already been telling you. And that this would be the K and that would be the H, and the scale factor or something there, and that's really wonderful and all. But it's these conditions that we immediately use here. For example, let's try the first R derivative of this wave function. Let's just take the derivative of the whole wave function. Well, that leads to a derivative of S. We already know what that is. It's there. So we work it out. Okay? Let me get going on the other screens here as well. So what you're getting there is the momentum operator. That's the way it's taught in quantum mechanics textbooks. Practically all that come out of Oppenheimer's notes, and then go into, actually comes out of Fermi's notes, and then Oppenheimer makes a book out of it, and then people copy that. That's sort of copy chain for this kind of stuff, the way of developing quantum mechanics, okay? So that's true for all dimensions, all coordinate dimensions. Okay, it's got everything exactly right.
I've got a few questions.
Yes. About the wave?
The first one, yeah, why would you pick e to the is over h bar?
Well, that's a bit of a nonsense. A good question. This is the simplest wave that you can think of. Now you start adding other components, right? I mean, you can do all kinds of things, make a whole series of things, and make any wave function you want, right? Mm-hmm. This is the most elementary Fourier component.
Okay.
This is maybe the best answer I could give you.
And so if it's simple and it works, why am I changing it?
Yeah.
Okay.
You build everything else from that.
Another way to say it is, let's take the simplest possible thing, see what it does.
Right.
Right? Well, it turns out everything else is going to be a combination of those things.
Mm-hmm.
So they're going to do it too.
Okay.
Maybe that completes
Yeah.
question, right?
Another question: what do we ever mess with S directly? It's all kind of a roundabout thing. We start with L,
That
get
is a
H,
really good question.
and then define S in
Yeah.
terms of H. But when do we ever use S?
I kind of let slip how we do that already. And when I talked about Heller and a bunch of other people's work, they're trying to solve problems in chemistry that are really just seemed intractable using ordinary methods of solving differential equations of Schrodinger. But even earlier, when they were doing the Bohr method of just doing the action integrals and demanding them be integers, that was called classical quantization. Okay, and what Rick was trying to do was figure out a way to get that out of that very thing, which worked okay for just an atom that was, you know, one electron, right? But you got a molecule, what the hell are you doing with all those electron vibrations, all that kind of stuff? Right? That's where he started to say, you know, we got to work with the action. That's where the action is. Okay, so that's, we're going to finish up here talking about that. This is the next step, though. Don't forget that we will have another variable here, time. What happens when you take the partial derivative of time with respect to our wave function? Bingo! Schrodinger equation. And you really have hit the jackpot on this one, because that is the correct Schrodinger equation for a fully relativistic Hamiltonian. This, you're just really lucky here. I mean, and of course got the thing on the wall here, right? This, talking about this Schrodinger equation. Space and time. Haven't quite, until I use this part here, gotten the ordinary Schrodinger equation, which is this one, of space. Okay, that's wrong. It doesn't have the MC squared and a couple of other things like spin, but that's a Dirac equation, right? We're asking for too much to get that at this point. Okay, now let's go ahead. As I say, that's what it is, psi dot equal h psi. All right, here's where we get Huygens' answer to that question, WTF. The idea of the minimum action is that if you're going to go to a certain point, then there is a minimum there, and if you deviate from it, it's always going to cost you more action. So if you deviate even a little bit from this curve, the first order, okay, there's already going to be a change, which if you do it a little bit differently, will cancel. So it's only when you're right on the extremum that you can move it just a little bit and it doesn't change to first order. It might change to second, but that's okay. It's when you have something changing to first order because you're off the path over here, and you go this way, it goes up, go this way, it goes down. Here, it only goes up second order by going this way, and it goes up second order going this way. So what happens is that the wave function tends to pile up on the extrema curve, making it the most probable path. In other words, making the world classical, making things obey Lagrange's equations. That's it in a nutshell, what's going on. That's why this Hamilton-Jacobi wave equation, really nice for handling whole families of trajectories like we're doing with the volcanoes of Io and all that kind of stuff. But the main thing that we're getting from all of this is the ability to see how Lagrange's equations are a result of a lottery. Okay, all of the other possible curves here, they don't satisfy Lagrange's equation. Only this one. only the one that gives you the extreme value for the phase accumulation and doesn't have destructive interference. Killing, as you would if you went along that curve there. Okay, so that's it in a nutshell. I mean, because the action is the quantum wave phase, then all of the funny stuff that happens with this, I'm getting all this going down here as well. All the funny stuff that happens with completeness, Feynman path closure, all that kind of stuff, okay, is automatic once you have found this. Now, if it turns out there's another extreme curve over here, then you get real interference between two classical situations. And that's, of course, very interesting. And that's what we look for. That's interesting quantum mechanics. But just traveling through space in a plane wave, this is telling you what the deal is with that. So, at this point, what we realize is, in order to make this thing satisfy a wave equation with a trapping, something that's trapping it, say, forcing it to go around onto itself, or live in a box of some kind, and always being running over itself. That is, the wave reflects off the sides, echoes and all sorts of things, and then it has to settle on a particular wave function. That is, well, that's what is called the Bohr quantization. It requires that the quantum phase and amplitude be an integral multiple of 2 pi. That is, the thing goes around a full 2 pi so that it comes back the same and doesn't cancel the thing that was there before it made that trip. So here's your Bohr idea of quantum mechanics. And that's all they had for a long time. The Schrodinger equation didn't come along for a long time, so they were always having to figure out paths and integrating them and forcing them to be integers, and that was a real chore, but it worked. It worked. Well, we're doing the same thing here, except we're letting the nature or a computer do it for us. So here's what happens, and this is something that I'll show you in just a minute here, examples of. This is why we color the wave functions according to the Lagrangian. This is one that's trapped. This is trapped in a box. This is just a good old harmonic oscillator that is doing the trajectory. And what's happening here is the phase is going through. When it starts at 0, it's red. When it gets to pi over 4, I turn it to orange. I plot it in orange. Pi over 2, I plot it in yellow. 3 pi over 4, I plot it in green. Pi in the same. That would be a really crude coloring scheme where I have about 6 different colors. More colors the merrier, but let's say that's what we're using here. In fact, that's what is being used in that particular picture. So what you you end up seeing here in this particular one, is it satisfies some sort of quantization because I only see red and the opposite color, cyan. In between there, on the nodes of the wave, they're all of the colors, they're all meshed together and to give you kind of a gray or something that doesn't really stand out, like the cyan here. So this is a wave that has a plus phase here and a minus phase here. That's 0 and pi. There's pi. There's pi. So this would be a wave that would be, this would be up and that would be down if you were to actually plot it out of the screen. Okay, that's a closed system. It has a quantized energy, a particular energy, so you have to hunt for that energy. That's the deal that was being done by Davis and Heller. Davis was a graduate student of Rick at Los Alamos, and that's when we started playing with. I figured, we got to do this color thing too. So that was then done. Now, what if it's like the volcanoes of Eel? Okay, that's open system. I can have any energy I want, and you'll see all the colors. You'll see a rainbow. That's what happens with that. Now that's interesting too. Being able to get actual quanta out is good. But this is a continuous one. It's some interest too. So I want to talk about that. These are the trajectories drawn up to a certain value of the action. So this is the wave front that's being displayed here. And that's something I'm going to animate, I think, just to give you a chance to see that. Here is the animation. I think I got it working before. There we go. Yes. So there's the explosion. And the trajectories are coming out, okay? But the wavefronts make a cat. See a little cat with the ears? The actual particles, they're just doing their thing. But the actual wave structure is next to that. And the question is, how fast does that go? What is it doing? Okay, let's reset it, just to heck of it. Pause, reset time equals 0. Let the thing go. Actually, I would like, I think, to pause and erase, and erase again, reset t equals 0. Okay, and then I'm going to pause this thing at a certain place. So this at first it's just expanding, but then it makes a cat. As soon as it touches there, it zooms, speeds away. The ears just separate with infinite speed and then slow down. Okay, so let me just go ahead and pause this one, and then we'll discuss what it is we've got here in terms of the algebra that we've already written. We've got a phase velocity, that's the dr dt, and that works out from our equation here, where we set ds equal to 0. We just pick a particular phase and just follow it. See how fast that phase goes in various places on the space that this wave lives in. Okay, and you can see I could make this any constant, but I'm going to get a phase velocity that is the ratio of the energy to the momentum. That is omega over k. Now you probably know that phase velocity, you should memorize this if you're a wave jock. It's omega over k. So as the momentum goes up, this thing slows down. As the energy goes up, it speeds up. Okay, but we're keeping the energy pretty constant, and we're looking at different momentum. Okay, as we come up to the top, the momentum goes to 0, and the phase velocity goes to infinity. And then as it drops, it picks up velocity and momentum faster and faster. As that happens, the phase velocity, the quantum thing that's underlying mechanics, slows down. Okay? Now that's quite the opposite of the group velocity. Quantum group velocity, this thing, is the gradient with respect to p of h. It's derivative of omega with respect to k. Not omega over k, but the first derivative of omega over k. That's Hamilton's first equation. Okay, that's really a cool thing. So these wave ears, these cat ears, scoot outward really fast here. Then they just slow down with the rest of the thing. So that, and of course the sphere of the blast wave, the classical blast wave, it just is going out, leaving trajectories that are interfering with each other. The ones that are on their way up are interfering with the ones on their way down at the very top of that diagram. Okay? So let me keep ahead on these two just to make the thing. This is just whimsical. You remember the Alice in Wonderland, the cat. And when he was done, there was nothing left but the smile. Lewis Carroll, an amazing person. In terms of he was sort of the Mr. Rogers of the Victorian era. Okay. He wrote for children. And he got taught a little bit of, I won't spoil the Me Too happened there as well. Seems it's everywhere. Distinguish the quantum stuff here from the classical waveform. That's very important. So you have a higher V group in this thing when this thing starts to pick up speed. So the group velocity, this thing right here, the classical velocity is what you're measuring there. You can't, as a classicist, see this one unless you've somehow colored the thing to get the phase. The phase of velocity is slowing down. So the actual P is the gradient of S. That's a Hamilton-Jacobi equation. Okay. So you're going to have a very low phase velocity down in that region. That's what that one over there and this one are saying. So this is kind of the best I can give to you right now of showing you what's the deep state behind the classical phenomenon. And showing you a glimpse of the Hamilton-Lagrange thing. That was an exact thing. We need to come back to that later. But you can look at it right now on page 2 of this, and also the last page of this set of notes here, besides showing Rick's artwork. He's done some really amazing artwork. Besides, this is on the second page. I would recommend, if you want to look at a quickie that really goes into that connection, I would have you look at this. I just gave a lecture this summer at Rochester, but look at that too. But this one is just a couple of pages, and you'll see a nice way to look at this. Now, as for this, I invited Rick to come and to exhibit his art. And this was from October 2002 to December 2002, so this is a long time ago now. And it was called Approaching Chaos. He was interested in quantum chaos, visions of the quantum period. Now what happened was, and I contributed a few of my pieces of artwork to the exhibit. I mean, and we had all worked together on a lot of this. But what we did was we closed the museum. As soon as we got done with the exhibit, they shut the place down. And there was even a cartoon in the school newspaper that showed a couple of students walking along. And one of them said, I didn't know we had a museum. And then the next frame was another student next to him. He says, what's a museum? What is a museum? It's gone. It's now, well, you know what it is. It's got a bunch of symphony hall sort of, I mean, it's a real big auditorium right across from the student union. Okay, well, as I say, we're at the end of the review except for complex variables. So we'll tackle that next week.